Okay, so it's 10 a.m. We're going to get started. The problem today on Mathematize, so the code is ZJ and X to log into Mathematize. It is kind of a review of what we did last class. The last class we ended with a four-sided dice. This time, as a warm-up problem, it is the exact same question, but it's a six-sided dice. So if you were paying attention last class and you understood what was going on, or you understood the conclusion we got to at the end, then this will make sense. So I'll give you 2 minutes to do that, and then I'll make some announcements and things. And let me turn on some lights in the back so you guys don't fall asleep back there. Okay. Okay, yeah, let's do a timer for a couple minutes. Okay, 40 seconds left. So put together some kind of guess if you haven't yet. All right, 10 seconds left. So remember, you can do 5, 4, 3, 2, 1 if you really have no idea, but you can take an educated guess based on what we did the last time. Okay. So, time's up. Let's see what the people say. Last class we had a four-sided dice. This class, it is a six-sided dice. Let's reveal the counts. Okay, 2, 5, 6, 2.1. And 10 people picked 3.5. The correct answer is 3.5. So the 10 people who did that did it correctly. Last class we did a lot of algebra, and we showed that the correct answer is, hopefully it'll be here in the blackboard. So we did lots of things. We showed that the correct answer is the expected value. So whatever the expected value is of the dice, that is the right y hat to guess. And it really comes down to this term, expected value of y minus y hat squared. It's a quadratic equation. You want to make it as small as possible. So which y hat should you pick? You should pick the expected value of y. And the expected value of a six-sided dice is 3.5. So last class it was 2.5 because it was a four-sided dice. And today it's 3.5. So the expected value of a six-sided dice, it's the average 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. Which is also the average of the first and the last number, which is 3.5. Okay. Any questions or comments about that one? Okay. We're going to build on this problem today. We're going to do a data version of this problem. So we're going to do like this had there was no data in it. We're going to do the exact same problem, but with data. A couple super quick announcements before we do that. One is that there is now a course website. It looks like this. It's almost like a Wikipedia style page. And these are all the things we did in lecture 1 as like a little bullet point. If you click on the little links or just mouse over them, it will bring up a page with stuff about that. So for example, that problem we did with regression and classification, that is types of learning problem example. This is the stuff with the movie. that we did. So this is a great place if you missed something in class, go check it out. And I have lecture 2, which is still in progress, so some of them just say to do. So like this one, I think is empty. It just says to do. But I'm going to try to fill them in as we go. And I also have links to the actual recordings of the lectures there as well. So hopefully that'll be helpful for you guys. Any questions or comments about that? Okay. Okay, let's jump in to the next problem, which is the dice problem again. So you must learn to love the dice problems. We're doing the dice problem one last time. Here is the dice problem, but with data. So we're playing the same exact game with the dice, except for we're going to pretend that we don't know that all 4 sides are equally likely. So all we know is it is a machine that outputs a random number, either 1, 2, 3, or 4. Maybe we don't even know that. It's a machine that outputs a random number, but we don't know anything about how it outputs a random number. And so instead, we're going to have a step 0. Before we had step 1, step 2, step 3. Now we've added a step 0, which is we're going to roll the dice n data times and write down the outcomes. So maybe we roll the dice, and it comes out a 1. Then we roll it, it comes out a 4. Then we roll it, it comes out 1 again. Then we roll it, it comes out 2, and so on. And we're going to do this n data times. So before we knew that the dice was equally likely to be all 4 sides, and this time we don't know that. We only have this data set of rolling the dice n data times. We're going to call them y1, y2, all the way up to yn data, which are the values that we got when we rolled it. That's step 0. And step 1 is to, again, come up with a y hat. But when you come up with your y hat, you're not allowed to cheat. Like, you can't use the fact that you know it's a dice and it's equally likely. You just can only use the data set that you have. Okay? So that's step 1. Step 2 and step 3 are identical to before. We're going to, once you've picked y hat with no cheating, so you can use the data set but nothing else, we're going to roll the die one more time, and then you're going to pay me y minus y hat squared dollars. So whatever y hat you picked is going to be used in step 3 to determine how much money you pay me. So that is the game. Very similar to the previous game, except now we don't have this data instead of what we had before. Okay. And the question is, when you do this before, we figured out that the optimal strategy is to pick y hat was 3.5 or 2.5, depending on the number of sides on the dice. This time, what is going to happen is going to depend on the number of dice rolls. And what I want you to look at is how much money do you pay me on average as a function of the number of dice rolls. So for example, if I only roll the die one time, you don't have a lot of information about the dice, so you probably owe me a lot of money. If we roll it many, many, many times, then maybe you get to really know that dice really well, and you can pay me less money. And the question is, what is the shape of that function, right? So how much money you owe me playing the game versus number of data points, what is the shape? And there are 4 options that are plotted here. There's a red curve, a blue curve, a green curve, and a purple curve. So the blue curve starts out a lot of money. Okay, really these curves should only be plotted for integer values, right? It should only be 1, 2, 3, but I connected the lines. So if you only roll 1 dice, you owe me a lot of money. If you roll 0 dice, you owe me a lot of money. But as you roll more and more dice, the amount of money you owe me goes down to 0. That's the blue curve. The red curve is the same as the blue curve, except it doesn't go down to 0, it goes down to some horizontal asymptote drawn in the dotted red line. Then there's the green curve, which goes down for a while, but then turns around. And last but not least, there's the purple curve, which is always going down, but it doesn't go down sort of smoothly. It has this kind of critical window behavior, where it's kind of flat for a while, and then it suddenly goes a lot down, and then it goes down a lot. And you have to think about this problem and what you know about data. How would rolling more dice help you figure this out? What do you think it would look like? Can you figure it out? So if you've been following along, there is a simple calculation you can do to figure out which of these curves it is. But I'll give you guys, say, like 3 or 4 minutes to think about it. What do you think it is? Feel free to discuss with your neighbors. Which one could it be? How is this problem different than the previous problem? What is the best guess? That's another thing you got to figure out. Find a strategy to guess the y hat. I will let you do all that, and you have these 4 options: blue, purple, red, or green. Okay, so let's take 2 or 3 minutes, and we'll do that. And feel free, again, to talk to your neighbors. Yeah.
These curves are estimations, right?
We're just looking at the shape. So which one has the right shape? They all have 4 sort of different shapes. We want the one with the right shape. Yeah. Okay, 40 seconds left. 3 people have voted, so maybe people are unsure. Take a guess. Take your best guess out of these 4. It's okay to be wrong, and we'll have time to think about it and vote again and discuss. So try your best guess on what you think it could be doing. Okay, let's see. I'm very curious what the votes are. Let's take a look. Reveal counts. Okay, we have 2 votes for blue, 5 votes for green, 1 vote for purple, and 9 votes for red. So a little bit split here. Out of 17 people, the biggest thing is red, which has just around half of the votes. So before I reveal the right answer here, let's talk about what is the right strategy for the y hat. Which y hat should you pick? How should you use the data you have to decide y hat? Anybody want to say what they thought of?
We can take an approach of mode, I guess.
Of what?
Of mode, like which number arrives the most times, and then we can.
Which one arrives the most times?
From that, the
I got it.
minimum
Okay.
number that arrives the most times, I think that we can pick.
I love this. This is a great idea. Okay, right hat should be the mode. The mode, that means whichever one came the most times of y1, y2, all the way up to yn data. Whichever one came the most times, we pick that one. That's the most likely one. That's what we're going for, right?
Yeah.
Great idea. Fantastic idea. Anybody have any other ideas? Yeah.
With more losses, we can calculate probabilities for each side.
Uh-huh.
So with that, it reduces to the problem which we did before.
Okay, I like this. So you're going to calculate, this is idea 1. Idea number 1. Idea number 2. Idea number 2 is to calculate, you're going to calculate P1, which is the probability of coming up 1, except it's not the exact probability, it's the estimated probability, P hat 1, and that's going to be the number of 1s divided by n data, and then P hat 2 is going to be the number of 2s divided by n data. So we're just going to count how many times did we get 1, how many times did we get 2. Call those things P1 hat, P2 hat, the estimated probabilities, all the way up to P4 or whatever. And then what do? How do I combine the P's to get y hat? What should I do?
The same thing that we did before.
What did I do before?
Just calculate the loss function.
And minimize it, okay. And when you minimize it, what is the minimum? That was the question we did before, right?
Yeah.
So it was 3.5 before. But what is it in general? If you have a dice with P1, P2, P3, how do you?
Keep taking averages of all the outcomes that we have. So like if we have 3 outcomes out of now, we can take the average, put it as the input for the next dice roll.
Got it. Okay, average. Right. This is the right answer to this question too, right? So y hat should be the average according to p hat. Right? So if you estimate the p hats and you do what we did before, that would be the average of whatever the p hats are, which is 1 times p hat 1 plus 2 times p hat 2 plus all the way up to, I guess, 4 times p hat 4 because it's a 4-sided dice. Right? That sum is the average according to the probabilities you estimated. And your idea is exactly this, or you want to just average them directly?
I don't know exactly what you're trying to get to, but what I'm saying is if we have rolled the dice 3 times as of now,
Yeah.
we can take the previous 3 outcomes,
Uh-huh.
take the mean loss of those 3 outcomes, and that should be our hat.
Okay. So do we average just the last 3 or all of them? Which one do you want to do?
Like as many as we have till now.
Average. Okay. So your idea is actually really similar to the first idea, except instead of doing mean, or sorry, instead of doing mode, you did mean, the average, or average, aka the average of y1, y2, all the way up to yn data. Right? So that's another idea. Great idea. Anyone else for ideas? Yeah. Which of these ideas is the best? Well, I'll tell you one thing. Idea number 2 and idea number 3 are identical. These two are the same. The same, right? If you just write down what is the formula for p hat 1, p hat 2, and so on, and you do this calculation, you're going to get exactly the same thing as the mean. You're going to be averaging them up. Because you're going to do 1 times the number of 1s you have, plus 2 times the number of 2s you have, plus 4 times the number of 4s you have. It is another way of doing the mean by just grouping them into buckets of 1s, 2s, 3s, and 4s. So ideas numbers 2 and 3 are the same, and idea number 2 and 3 are the optimal thing to do according to the calculation we did before, which we said if you knew the whole thing, the optimal thing to do is the mean, and this is our best estimate for the mean. So this is the best estimate for the mean. Okay, and so the reason mean is better than mode is because of the calculation we did last class that we did in the warm-up problem this morning, which says that the whole thing is going by the expected value minus whatever the y hat you picked squared. And so you want to make that as small as possible, you should choose y hat to be the mean. The mode does not appear there. If the mode is equal to the mean, then great, but if the mode is some other thing, then you get the expected value minus the mode squared, which is bigger than 0. So you don't want that, you want the mean. Okay, so ideas number 2 and 3 are the same, and they are taking the data and using it to sort of pretend it's a random variable and estimating its mean.
Sorry.
Yeah.
But in this case, the n is matters.
Does the n matter?
The n data is matter because
Uh-huh.
you have no estimator of the n value because it must be not a specific value of n.
Uh-huh.
So we have the average of calculating is not the correct answer. I think.
What? So you're saying I can't do the mean, or
I think it would be the correct answer or the best answer
Uh-huh.
if we have the specific time of n.
Uh-huh.
But in this case, because we have a large amount of n and there is no specific data for n, I think the average would not be the best answer.
Okay, maybe there's a confusion about the question. So we're given n. Somebody tells us at the beginning n. So somebody says in step 0, they gave us dice rolls, and we can count them. We go 1, 2, 3, 4. We say, okay, you rolled 4 dice. Like we know n. So in the problem, we're given n, and we're given the list of n dice rolls, and then the question is use that to construct y hat. Is that the same as what you were thinking, or were you thinking something slightly differently?
Mean n is specific amount.
N is a specific amount. It's the number of data points we have. We open up our data set, we count the rows, and then that's the number.
But if it was specific, but it has a large amount,
Uh-huh.
a large value, I think it would be difficult for calculating as average.
Okay, so I get it. So you're saying this quantity, we can calculate it, but you're saying it's difficult if n is really large because you have to sit there all day and add up numbers.
I think it's not, the accuracy is not correct.
The accuracy, what do you mean by it's not correct? So the claim is that it's the best possible thing because we proved last class that whatever you do, you're going to get the expected value of y minus y hat squared. So all you got to do is pick y hat to be as close to the mean as possible. And how are you going to get as close to the true mean as possible? You're going to use this empirical mean, averaging the data points you have. Yeah. So what's, maybe I'm not understanding your objection.
Let's continue maybe.
Okay, so like, is it that you think we can't calculate this, or is it that you think you can calculate this, but this is dumb, we should do something else?
I think for the large amount of n,
Yeah.
the average is not, or the mean function is not a good choice.
It's not good because it's not the most accurate, or it's not good because it's too much work to do?
I think the first too much to do.
Okay, this is great. We're not worried about that at all. This is a fantastic point. I don't care in the thing, this is a really good question to have. You are paying me according to how big y minus y hat squared is. You do not have to pay for the computers you used while you were running the experiment, or the slave labor that you had to enlist to come up with y hat. All of that is free. So this is a really good point. We're not worried at all in this course about, or at least for this problem, computational complexity of any sort. So you can do as much work as you want, and it does not affect how much you pay. The only thing you care about is y minus y hat squared. That's it. So I think it's a good clarification of the problem. It's okay to do a lot of work here, and in this case, doing the mean is perfectly a valid operation. Okay, so we're going to do the mean, and the question is, what does the graph look like? About half the people think it's the red curve, which looks like this, kind of goes down to a plateau, and half the people think it's the, what was the other ones? The green and the blue were quite popular. So the green goes down and then goes up. So if you chose green, it means you think that, there's a sweet spot where if you roll, this is just a cartoon, but if you roll 10 dice, that's really good. And then if you keep rolling dice, it gets worse and worse. And that is not correct. So let me reveal the correct answer. The correct answer is the red curve. So just over half the people got it right. It really does go down like this. And what is the plateau value that it goes down to? Like, what is this dotted horizontal line? That is the amount of money that you pay if you know the dice perfectly in what we did before. So I could have said, and I did this last class, I said, what is the optimal value and how much do you pay? And we discovered that last class in our proof, which is, again, nicely written on the website if you want to see the proof. The amount of money you pay is a sum of two things. One of the terms is the expected value of y minus y hat squared, but then you add on this other term, which was the variance of y. So for a four-sided dice, that's 1.25. No matter how good you are at estimating, even if you have the expected value perfectly correctly, you will still have to pay $1.25 on average every time you play this game. And that is just because the dice is random. Even if you have the perfect estimate of the mean, you're still paying money from the variance. And that is why you will never go down by this. You'll never go down to zero. The most you can do is do this. So that's why you have this horizontal thing. Last class we gave this a name. This is the irreducible error. The irreducible error. Irreducible error. And you will never ever exceed the irreducible error on this dice, even if you're the best data scientist in the world. So this is something to be aware of, is that typically you have these situations where you're trying to get down to some minimum, but that minimum is not zero. Okay. In the next little bit, I'm going to show you, it's a very simple calculation, using the exact same math tricks we did last class, to prove the shape of this curve, that goes down smoothly like this. And you can calculate exactly what it is. And then we will know exactly what is the effect of having data instead of having the true value. That's the effect of kind of like noisy observations, right? These observations are not perfect. We're going to be able to quantify that into an actual mathematical formula that tells you how is the red line, how is it going down to the dotted red line, which is the limit. Okay, any questions or comments before I jump into that? Okay, let's look at this calculation. So what we're trying to do, and let's start a new page here. So again, this is all typed up now on the website, on this article called How Variance Contributes to the Loss. And I'm basically going to show you this. So the loss function we have is the loss function for some given y hat is equal to y minus y hat squared. Okay? And we showed that if you do the expected value over y, so once you've chosen y hat, this decomposes as the variance of y plus the expected value of y minus y hat quantity squared. This was last class. So the first line is the loss. That's like how much money you actually owe me for a given experiment. And then the second line is averaging over the value of y hat, y, how much money you owe me. That was the calculation we did last class. And it's a quadratic equation which has this minimum at the expected value of y, and it has this irreducible variance term that you will always owe me no matter what. Okay. This is for any y hat this is true. Now the y hat that we are picking is a function of the data. So, but y hat is actually y hat of y1, y2, all the way up to yn. I won't write n data, I'll just write n to save a little time, right? So the y hat we pick actually depends on our data. And it depends on our data how? Well, it's the function 1 over n times the sum of the yi's, right? It's the average of the yi's. That's the best possible thing. So y hat is the average. Let's put that in. And now we see that the expected value of y, well, it's the loss. It actually depends on y hat is actually a function of y1 to yn, right? So you told me y1 to yn, and that's how I made all my decisions. So it's the same formula as before. And we're going to have this formula. 1 to n of yi. Oh, I wrote them in the reverse order. Okay, let's do it like this. Expected value of y minus this all squared. So whatever they come out to, if they come out really close to the mean, then great for you. Good for you. You're not going to lose a lot of money. If they come out really far from the mean, then you're going to lose a lot of money. Great. Now I think this is the like key thing. The data we got itself is actually random, right? When you roll the dice, that's generating some data. So I can do the expected value of this whole thing. Okay, expected value that I'm so excited about that I wrote it with 4 lines on the E. Okay, only 3 lines on an E usually. So we can do the expected value of this whole thing. And what do I mean by do the expected value? I can do the expected value averaging over y1 to yn. So for a fixed y1 to yn, we know what happens. What happens on average when you average over y1 to yn? And on the left-hand side of this equation, that's exactly what we want. That'll be the expected loss. So this is going to be the expected loss. And it's averaged over all the data sets. So it's kind of like, I'm going to come up with a strategy. What strategy will minimize my loss on average, averaged over all the possible things that could come up in the data? On the right-hand side, let's do the calculation. So one of them is just a constant. The variance of y is a number. It's like 1.25. So that just comes right out, the variance of y. And we're left with the expected value of this sum all squared. And I'm going to write it backwards. I'm going to write it like this, because I want to write it like this. yi minus expected value of y. Since it's inside it's inside a squared, it doesn't matter if you write it forwards or backwards. It's the same thing squared. Okay, so now we've got to calculate this thing. This thing is the expected value of something squared. Last class, I made a big deal out of a certain formula called the Pythagoras formula for random variables that says if you have the expected value of a sum squared, a plus b squared, you can write it as the sum of the expected value squareds. And you can do that as long as the individual terms are uncorrelated. And just by chance, I guess it happens, not by chance, we set it up exactly perfectly so that these things are uncorrelated, right? Every term is mean 0. So what I'm going to do is I'm going to bring in the expected value of y into the bracket. So instead of averaging the y's and then subtracting the expected value of y, I'm going to subtract the expected value of y from each term and then average them. And that's okay, because the average of a constant is the constant itself. So this is okay because, let's say, the 1 over n times the sum of a constant is equal to the constant. Okay? So you can put it inside or outside the sum. It's the same no matter what you do, because the coefficients 1 over n add up to 1. Okay. And now it's a sum of terms. I have a 1 over n. Let me move the 1 over n out. It's 1 over n squared. So if I move the 1 over n squared, I can move it outside. It hops out to give a 1 over n squared, right? Because it was squared from the 2. And now it really is a sum of terms, and I'm adding them up and I'm squaring them. And each term is mean 0. Individually, each term is mean 0. the terms are independent, right? The y1 and y2 are two independent dice rolls that have nothing to do with each other. And so they are uncorrelated. If you do the expected value of 1 times another one, it will be 0. In fact, it'll be 0 times 0. You see, the expected value of the first one is 0, the expected value of the second one is 0, and they're both independent. So by Pythagoras, this is the last line we're going to do. Let's do it in purple, and let's leave a little bit of room. This will be, so the variance, this is the irreducible part. We have the 1 over n squared, that came out of our 1 over n. And now the expected value of the thing squared becomes the sum of the expected value of each individual thing squared. So that's Pythagoras. Last time we saw Pythagoras for 2 terms. This is Pythagoras for n terms. Of course, that works perfectly fine. Okay. And this quantity, the expected value of y minus the expected value squared. This one has come up a few times. That one has a name. Does anyone know the name of that thing? Yeah, go ahead.
Expected loss?
It has something to do with the expected loss. And that's how it came up last class. Let me scroll up to last class. So it was the exact same term that was the first term in the expected loss. We basically did a very similar calculation last class. In last class, this was the irreducible part. The expected value of y minus the expected value squared. And that is exactly what we call the variance. That's the variance of our integral. This is why variance is what it is. Like the people who invented variance didn't just like make it up. They like saw this thing appearing in their calculations over and over again. And they're like, this is really annoying to write. Let's give it a shorter name. Okay, so this is the variance. And so it would be the variance of yi, but the y1, y2, y3, they're all the same, right? They all have the same variance, which is for a 4-sided dice is 5 quarters. It just depends on what type of dice you're using. It doesn't depend on the individual thing that's been averaged over. So this thing is the variance of y plus 1 over n squared, and then you have the sum of the variance of y. Look at that, the same dice we're using. Okay, and this is one thing I'm very good at. If you give me the same number and you tell me to add it up n times, 5 quarters plus 5 quarters plus 5 quarters plus 5 quarters plus 5 quarters, n times, I'm very good at doing this because I know that this is multiplication. Adding up one number n times is the same as multiplication. So the variances got added, so the variance of the whole thing was n times the variance of an individual thing. But then when we did the 1 over n, when we averaged, that became a 1 over n squared, because variances have this square term in it. So what is the overall effect? We have a 1 over n squared fighting an n, and so the final answer, let's do that in blue, is the variance of y plus 1 over n also times the variance of y. And this is exactly the function that goes down like 1 over n, but approaches a constant. So this first variance of y, this is the irreducible error. Irreducible error. That is the dotted red line. And this second one is how we approach it, how we go down. As we get more and more data, this will go down to 0. And so I'm going to call this term the loss due to variance. Loss due to, I'm going to call, say, data variance. And in this particular problem, it was literally the variance of the sum, the variance of the average, which is shrinking like 1 over n. And so our total loss, this was the total loss, the expected loss. Over here, the expected loss averaged over all the data. I'm going to call it L. So it's really an expected value over the data and y, right? So you average over the one outcome where you pay, and you average over the data as well. It has 2 parts. It has an irreducible error part, and it has a loss due to variance. And you can see that as you roll more and more dice, that loss due to variance goes down to 0. If you knew the dice perfectly, this would become 0, but you still have that irreducible error you can never get rid of. So this kind of decomposition, you're not going to have to do it by hand, and in real situations, you can't even calculate it because your system is more complicated than just dice and averaging, but this decomposition always exists. So you should always think of, when you have a loss, there's an irreducible error part, and there's a loss due to variance. And both of these things are contributing to your total loss, which you're trying to minimize. Okay, any questions or comments about any of that? Okay, once again, it is typed up nicely now on the website, so you can read. If you don't like the written note, you can go read how it's written there. And so this is a good lesson about the effect of data versus the effect of no data. Okay. Okay. Let's go to the next problem. Right, and the next problem is exactly the thing from that video, which it did not open. Okay, let's see if we can find it. Okay, let's try. Okay. So this is the thing that we're going to do next, which was from that video that you were supposed to have watched. And let me make it big like this. So we're going to move on to this. Before we do, last chance for questions or comments about the dice example, because in the dice example there were just y's, and this example really is identical to the dice example, except instead of just y's, there are now x's and y's. So we're graduating from having a y with no data, now then we did a y with data, and now we're doing x's and y's. And we're going to fully understand what's going on here, and that's going to help you think of this spectrum of overfitting and underfitting. Okay. Any questions or comments before we start? Okay, so let's jump into it. So I'm going to turn off this error. But so hopefully you saw the video and it made some sense. But essentially what we have here, before anything else, I'm going to turn everything off. This and this. Okay. So you're given, in this problem, you're given a bunch of x's and y's. So instead of just being given a list of y's, you have x's and y's. And okay, maybe let me see. Can I do this on the screen? Okay. So you have x's and y's, just like was in the video. I'll just do it on track. So before we had just y's. This is a set of y's. Now we have a set of x's that go with them. And the y's, I said it was a cannonball, so the y's represent how far the cannonball goes. And the x's represent what angle you put the thing at. So maybe, you just watch some people shoot the cannon and you write down these x's and y's. I don't know, this one's 0, this one's 45 degrees, this one is 20 degrees, and so on. And you can really think of these are like dice, except for the dice, instead of just having a y, also have a label that tells you something about the dice, right? So the x is supposed to tell you some information about the dice, and the y is the outcome of that dice. That would be another way to think about it. And here is the set of points I got. I think end data is 30 here. It's too zoomed in to see. Can I zoom out even more? There we go. End data is 30. So there's 30 cannonball shots, and we have to use those cannonball shots to figure out the true function. And the true function is here. It's this blue function. If you know physics, this is the function sine of 2x. That's how far, if you shoot a projectile at a fixed velocity, how far it goes is the sine of twice the angle. In real life, of course, you don't know the blue function, right? This is the cheat we're doing. You do not know the blue function in real life. You only have the data. We are just using it in the same way we were using what we knew about the dice to say what is the best value. So if we knew the blue function, that would be the best possible estimate. That is the mean value for any given x is that blue function. That is the best possible estimate. That's what we want to do. And in real life, you don't know the blue function. So we also know that the best thing we can do is to do the mean. So ideally what we want, and that's the blue function, so we really have this decomposition, that the y value is given by f of x. This is the true function that we're looking for. True function. Plus epsilon, that is the irreducible noise. So in the dice, we only had the epsilon, right? We had y as epsilon, there was no x. And now we have this f of x, which is the true function. And we want to find the best possible estimator. F hat of x is the expected value of y given x equals x. And y is the expected value of the best one, again, because you can apply the exact same argument we did before. In general, the expected value of the square loss for any f hat of x. Let's say given, let's do the expected value given capital X equals lowercase x. Again, it has this decomposition, the same decomposition we've seen again and again, the variance of epsilon, plus f hat of x minus f of x squared. So there you go. This is the exact same thing we did before, but now we're applying it to a problem where there are x's, and that is the data science setting. So that's why we did those examples before, so we could understand where this equation comes from, and it's not just magic, right? It really came from those calculations. All right. Any questions or comments about this formula? Okay. So we want to come up with this f hat. The f hat, the best f hat, is the one that estimates the mean. And how did we do it in this video? Of course, there are many possible ways you could come up with an f hat, but the way we did it is we picked some point, and then we said, let's average everything within some window of that point. So you can, for example, if you set the point to 45 degrees, then you can average the 5 points, this point, that point, this point, that point. Maybe there's only 4 points. Okay, there's 4 points, and you average them, you get that point as your average. That's your f hat. F hat of 45 degrees is where this purple dot is, just below the blue dot. That's your f hat. And if you draw the whole function, f hat of x is a function that looks like this. It's very wiggly waggly, it goes up and down and up and down. And that's because as you move around, you're averaging different points, right? So as you slide it around, you're averaging different points. So over here, there's not many points here, right? There's only, I think, 2 or 3 points. And so this point is playing a lot of influence here, because it's the only point in that neighborhood, right? Whereas there's some regions where there are a lot more points, and over here, all the points sort of share equally, right? There's many points, we average them, and we go over here. Okay. That is the setup. That's the purple function, which is our f hat. The blue is the real f, the f true. And our goal is to make them as small as make the difference between them as small as possible by minimizing the squared difference. Any questions or comments about the setup? So I know you probably saw the video already, but was there anything that was unclear or something like that? Okay. So let me put to you the question, how should we set the size of the window? Should we pick a very big window, or should we pick a very small window? And this was discussed in the video, so if you watch the video, you will know already the answer. But to see what you guys think, I have put it into mathematize. So I call the window size, I call that delta. Delta is the Greek letter for D. So D, this stands for distance, the distance between the point and the edge of the window. So is it better to pick a small delta or a big delta? And remember, the reminder is that small windows contain very few data points, and big windows contain many more data points. So what is better, a small delta or a big delta? And I'll just give, seems like people know the answer, so let me just give 1 minute. 1 minute here to start that. Okay, 1. Okay, 10 seconds. Almost everybody's in already. For the last few people, put in a guess. Okay, let's take a look. What you guys see is basically asking, did you watch the video? 15 people out of 16 said delta should be neither too big nor too small. There's this Goldilocks zone, and that is the correct answer. So very well done. It means you guys watched the video. To me, this is like the simplest problem where you can have some crazy thing like this happen. This is totally nuts to me. Why is there, how is it possible that small and big, it's not one is better? Like before, right? The question I asked you guys before was this one with the graphs, right? This one. Can I click on it and make it big? We had these graphs, and the answer was it was steadily going down. Like more dice is better, right? So isn't it better to have more dice? Isn't that always better? right? And actually 5 people picked the green one when I did this question. So those people were thinking ahead to later in the lecture, where it does kind of go down and then go up. But it doesn't go down and then go up with the number of dice rolled in this problem. It does go down and go up with the delta. So how is it possible that the delta is having this weird roll? And so some people's instinct is that delta should be as big as possible, right? If you make delta really, really big, then you're averaging more and more points, right? If you make delta, the window, really, really big, you're averaging a lot of points. And averaging a lot of points is exactly why this thing is like having more dice. So you're getting a lower loss, right? And you're getting lower on that variance term specifically. So this is, I think, intuition number 1. Intuition number 1. This is at least my intuition, is that you want to make it as big as possible. Of course, this is wrong. Intuition, that big delta is better. Big delta is better. Okay, and it turns out this is wrong, but there is a kernel of truth to it. Having a bigger delta means you are using more points. So I'm going to let nx be the number of points such that xi minus x is less than delta. That is the number of points in the window around x. So number of points in the window. Number of points in the window around x. So for a given delta, how many points do you have? And the thing is, nx really is getting bigger and bigger the bigger you make delta. So nx, it goes up, let's say goes up as delta goes up. So as you make delta bigger and bigger, you get more and more points in every single window. And the truth is, the variance of the function f hat that we chose, the variance of the f hat, is also shrinking like 1 over nx. Okay, let's say times a constant. Why is the variance of f hat like 1 over nx? Well, it's exactly because f hat of x is the average of all the points in the window, right? So it's the sum from I equals 1 to nx of the yi. You average the y values in the window, and you have nx points that you're averaging. So why is it true that the variance of f hat is 1 over nx? That's exactly the calculation we just did a minute ago for the problem with the dice rolls. Right? When we had just dice rolls, we had literally this formula, right? Nx was given to us, it was some fixed amount. In this problem, because there are x's and y's, we are playing with the x's, and that is what determined the nx. So it really is the same, it's a harder version of the previous problem. In the previous problem, the n data was given to you. And in this one, you get to choose nx. And you would think, let's pick nx as big as possible to make the variance term as small as possible. And indeed, the variance really does shrink like 1 over nx. It has that smoothly thing going down to 0. The calculation is exactly the same as before. And you really can decompose what we did before, this decomposition of the irreducible error plus the difference here. Just like before, we can take the expected value of that, and there's going to be a variance term. So this was, so far we've done the expected value over y. Now, let us take this equation, and let us do the expected value over the data. And when you do the expected value over the data, you really will get, so this is all when you average over the data, right? Okay. So you really will get that the, let's do it in blue. So the expected value over the data and y of the loss function of our estimator f hat. Let's do it at some given point x, just to make life a little bit easier. It's going to have 3 parts. There's the variance of epsilon. This is the irreducible error that we always have, we can never get rid of. The irreducible error. Okay. Plus, there is a term that is the variance of that hat. That is exactly what we did in the previous problem at the beginning of class today. We said if you have some data, you're going to end up with 2 parts, the irreducible error and the variance due to the data. This is the variance term. The variance term. But there is one more term in general. There is one more term in general. And that term can be written like this. The expected value of f hat of x minus f of x, all squared. This term is the bias term. The bias term. And the intuition I said, that having more bigger windows, it really does shrink the variance term. It really does shrink the variance term. So the number of points, the variance is like 1 over nx. So in our situation, the variance, we have variance of epsilon, we have 1 over nx. That really is like the variance, okay, times some constant, the variance. And you really are shrinking this term. The bigger you make the window, the less variance you have. This term is shrinking down to nothing. So that's great. That's why a bigger window is good. But there's this other term, the bias term. And I hope you can see sort of where it comes from. So I won't do the detailed derivation because I think you guys have had enough of the Pythagoras theorem for random variables. But if you just take this formula and you write it out, you do the expected value, it's the difference squared. And to make the terms mean 0, you're going to end up with, because you're subtracting f, and you should be subtracting the expected value of f hat, you're going to end up in the Pythagoras formula exactly with this difference, the expected value of f hat minus f. So we saw that come up in the simpler problems. It's the exact same argument here. That bias term, it comes out. And we did not have that in the first example we did today. So this is now with x's and y's. We did not have that in our first example because our estimator, the y hat, was exactly the mean of the y's and was unbiased. So the mean of the y's happened to be the same as the true mean for doing the simple average when we only had y's. And so there was no bias term. And in that situation, when you know the bias is 0, then you can shrink the variance forever and ever, make it go down to 0. But when there is a bias term, then you cannot just shrink this for free, right? Shrinking this for free might cause this term to go up, and that is the bias variance trade-off. In this situation, let's try to estimate what we think the expected value of f hat is. Let's try to think of that. So let's do the expected value of f hat of x. And we would like it to be, ideally, it should be f of x, right? If it was exactly f of x, that would be unbiased, and then that bias term, the difference squared, would be 0. That would be lovely if that was true. Unfortunately, I think it's not that. And I think it's actually another very simple formula. It's the integral from x minus delta to x plus delta of f of u du. And it's averaged of size 1 over 2 delta. It's something like this. Why is it the integral from x minus delta to x plus delta? Well, that's exactly saying when we do this averaging, right? When we do this averaging, we have some window that we're choosing. We're counting all the points that are in this window from x minus delta to x plus delta. And all of those points could be there. We're averaging them all equally. Whenever a point appears there, we're averaging it up. What is the height of that point? Well, on average, it's f of u when you see it at the point u. So we're averaging all the points f of u that live in the region x minus delta, x plus delta. Okay, we're also averaging the epsilons. There should be an epsilon for each point, but the epsilons are the irreducible noise. They do not affect the mean, right? On average, it's f. And that is why we have this formula over here. It's the integral from x minus delta to x plus delta of f of u. That's like adding up all the points in the region, x minus delta to x plus delta. And then 1 over 2 delta is saying, okay, divide, to average it out, right? Any questions or comments about this formula? You guys okay with that? Okay. And so this is the thing, right? The integral of f on some region might not be the same as the value at a point, right? And in fact, if you look, what is the integral of the function f, say, around 45 degrees? Let's do the integral of the function f from 30 to 60 is the area over here. We divide by the width here, so we're getting the average value of the function f on this window. What is the average value of the function f on this window? Well, it's some kind of a little bit below the top value because these things on the side are pulling it down a bit. So when you average a function on some window, the concavity of the function, if it's concave up or concave down, will matter, and it will bring it down in this case because the function is concave down. So in fact, you can show, and I did this in the notes, but I won't do too much here, right? I'll just skip to the final answer. You can show that this is approximately, by using a Taylor series, the second derivative of f of x times delta squared. Okay, it comes out with delta squared over 6. So the bigger you make delta, the bigger this is, right? The bigger the difference between f and this integral is. If you have a very big window, you're including parts of the function that are very far from f. And it's proportional to the second derivative of the point. So if you have something that's concave down, like over here, then you will consistently underestimate. That purple curve will always be under the blue curve. Or not always, but on average, right, it will be under. And this depends on delta squared. If you want to see why is it delta squared and why not delta, you can read in the notes. So if we go back to our whole decomposition over here, we had the variance plus 1 over nx plus, we're doing the bias squared, so this is the derivative f prime of x times delta squared divided by 6. All squared. So that's like a delta to the 4. So if you make delta really, really big, you're going to make the nx tiny, but you'll make this term really big. And that is why you cannot just make delta as big as you want. You can't make delta as small as you want because this term will explode, and there is a balance to be had. I'll do one more thing, which is nx is the number of points in a region of size 2 delta. Nx is also approximately, on average, delta times some constant. Right? The number of points, you take like the whole region, how many deltas fit into it. So the bigger you make delta, the more points you have. So you can actually replace this nx, you can replace it with delta. So really this is the final formula, the expected value for the loss. It's the variance, the irreducible variance, plus there's a term that's like 1 over delta, and then there's another term that's like delta to the power 4. And this is really what is going on. It's the balance of these two terms that is causing this Goldilocks phenomenon to happen. So let's make a new Desmos and plot what this looks like. So I'm going to use 1 over x. Okay, we're going to do it times c, make a constant c. So there is the function. Let's only look at deltas that are bigger than 0. So in Desmos, you always have to put an x as your variable. So that's the variance term going down to 0 forever and ever. Okay. Let's add on the irreducible variance. Let's call that a. A for, all right, I should call it I for irreducible. That's much better. Okay, I. So there's the irreducible variance plus the bigger you make the window, the bigger you make delta, the less variance you have. It's going down like this. But then there's another term that was like plus x to the power 4, also times some other constant d. And now, when you add on x to the power 4, you get a curve that looks like this, right? X to the power 4 on its own is blowing up forever and ever. And now there's a balance between these two terms, and that is why you get this U-shaped situation going on. So can I zoom in here to see the U-shaped curve very nicely? And so depending on what these constants are, depending on what the constants in front are, you have some spot in between that is the sweet spot where these two things are balanced perfectly, the variance and the bias. And that is what you want to find. That is why, in this window, there is, the answer to the question is there's a Goldilocks zone, which you guys all knew from watching the video. Okay, so it should be neither too big nor too small. There's this sweet spot in between. I think with these parameters, it came out to like 11 in the video. And you can calculate it exactly by figuring out what are these constants. One of them is going to be like x to the 4, one of them is going to be 1 over x, and then you minimize that. That gives you some theoretical minimum value on this curve. Okay. Questions or comments about that? So now you've seen in mathematical detail kind of what was explained in that video. That was a kind of a rough, high-level version, and now you've seen the more in-depth version. Questions or comments about any of that? Okay, let's connect this to what was in the other videos that you had to watch. And in one of those other videos, they had a graph like this, and they had flexibility was on their axis. So they had flexibility on the x-axis, and then they had the mean squared error, the error, on the y-axis. And so far, we've made a graph like this, where it's not flexibility, this is the size of delta, right? Delta is either big or small. And the question is, which is which? Is delta big more flexible, or is delta small more flexible? When they were talking about flexibility, they said more flexible models do badly, less flexible models also do badly. And they had some pictures here. So the orange dot is their least flexible dot, that's the straight line. The blue dot is their Goldilocks spot, that's this blue one. It goes like this. And the green dot is the one that goes up and down and up and down. So the question is, what is the correspondence between flexibility and delta? Because it doesn't, like, why should, you know, what's going on here? Like, is a big window more flexible or a small window more flexible? What's the correspondence? Okay, and I'll give you guys a couple minutes to do this one, to think about that one. And I will present. Okay, so, and the options are, tell me what higher delta means. So bigger delta, is that lower flexibility or higher flexibility? Or maybe you think there is no possible way to think about it in terms of flexibility. Okay, let's have a couple minutes for that. That's not what I want. Yeah.
So overfitting is called being more flexible?
In this video, they were saying if you are more flexible and you have this high error, that was overfitting.
Okay.
Yeah. Okay, there's like 50 seconds left. Maybe I gave you guys too much time for this one, but some people still haven't answered, so.
Whose time does it work?
I think it doesn't really work. Yeah, this is.
It's not raising the temperatures.
I think the thermostat is underfit to the temperature of the room. Yes. Okay, 10 seconds left. Okay, let's look at what people thought. Which one is which? And let's reveal the counts. Higher delta means lower flexibility is the popular one by a margin of 14-3, and that is also what I think. So yes. And when you have this low flexibility, so first of all, I think this flexibility thing is a weird way to think about it, because it's really hard to say, like, in what way is the model more or less flexible. So, like, if you look at this picture, where is the flexibility? I guess you could make some argument that's saying, oh, the function, when you have a really small window, when you can have a really small window, the function is more able to jump up and down very quickly. And that is more flexible, because it can move around faster. So that's maybe more flexible. But it's kind of a strange, like, I don't really see the flexibility. It's sort of like, if the space of functions that you can do is bigger, that is more flexible. And sort of the functions here are messier when you have a small window size, and so it's more flexible. And this is called overfitting. And you can see overfitting, we're really chasing down these points that we were given. And by chasing down the points we were given, we are minimizing our bias, right? So the points we have are on average correct, but we have a large variance. And so I really think of it, I think instead of thinking about it in terms of flexibility, it is better to think in terms of bias and variance whenever you can. So going back to this, in the video they talked about flexibility. I think it really should have been something like amount of bias, amount of variance. That would have been more mathematically correct. Flexibility, when you have a model with like number of parameters and you can think about flexibility, then flexibility is a helpful way to think about it. And so over here, this is really the situation where you have high variance and low bias. And you can see that, and in fact, that's what I did in the video. I animated what would happen if you sort of regenerate the data, right? And so the model will jump all over the place. Sometimes it's high, sometimes it's low, and it's doing these big swings. That's high variance. And that's how you can see the high variance term appearing. And another way to say it is like the effective amount of data you're using for each point is small. That's high variance, just like the dice problem. Not a lot of dice would lead to high variance. And on the other hand, you have a very big window size, like this. That would be low variance, because it's not moving a lot, but high bias. Again, because you're averaging points that are far away, and that leads to high bias. So you can really see what is causing the bias here. In more complicated models, you don't really know why it has bias. You just know that it is biased because of the way that the error is. So this is a really nice problem, because you can really visualize why there's bias. You have such a big window that you're doing that you're taking points that are far away. Those points don't match the real point that you want. Okay, so that's underfitting, overfitting, and bias. This leads us right into the next topic for next class, which is going to be, okay, so in real life, why don't we just plot this curve and find the minimum? Like, it's very simple. Like, why is this an issue that people worry about? And I just showed you how to do it. Like, I had this graph. I said, you plot the curve, you find the minimum, you're happy. Why is this an issue that people care about? And that is the next mathematized question. Tell me something about real life. In real life, why doesn't this work? And the reason is because we don't know blank. There's something we don't know. And I'll just give you 1 minute to put in your best guess of what the blank is. Okay, by the way, I think I didn't use this word in class yet. MSE is mean squared error. We had squared error. And then we took the mean, that's the MSE. Sometimes people take the square root at the end. That's called the root mean squared error. The reason to take the square root is because then you convert the units back to whatever they were originally. So the mean squared error, if you're doing dice, will be in units of dice squared, right? Like whatever the value on the dice is, it'll be squared. And the root mean squared error is back into the units of dice. So if you say I have a root mean squared error of 2, then you're off by like 2 typically. Whereas if you say I have a mean squared error of 2, then you're off by square root of 2 typically. So that's why the square root is sort of interesting. Okay, let me give you more time here because I talked while you were supposed to be thinking. Let's do 2 minutes. Okay. Why can't we just plot this function, this is the mean squared error, and find the minimum, and then call it a day? Why can't we just do that? Okay, 40 seconds. If you don't know why we don't know, then put in I don't know. IDK. A good I don't know answer. Okay, put in something. The time is up. Let's see what people said. Any interesting answers? We can't just plot it because we don't know what? The true value. The true function. This is great. The true values. Okay, so anybody who put true somewhere in there, the theoretical value, that is a fantastic thing. In real life, of course, you don't know the blue curve. And the way we did the error is we said, take the difference between the purple curve and the blue curve and square it and add it up. But of course, if you knew the blue curve, then why would you be doing this? So in real life, you don't know the blue curve. Let me see where's the error? Error visualization. So that's how we've been calculating the mean squared error. We know the blue curve, we figure out the purple curve that we got, we calculate the difference between them. But in real life, of course, you don't know the blue curve. So you cannot do any of this stuff. So why have I been telling you all of this stuff? Is because there is a method to try to estimate what it is. Try to estimate the error even if you don't know the true curve. And that's what we're going to do next class. So you won't know this exactly, but you will know it approximately. And this is becoming too complicated for Desmos, so we are switching to the big guns of the course, which is Python. So this will be, next class we'll do this. It's the same exact problem we did this class, y equals f of x plus epsilon, and then we have the same kind of graphs we had today. Let me see if I can center them correctly. I don't want to do that. I want to do this. Okay. So that's the exact, very similar to what we had last time, data and the true mean. The nice thing is in Python is you can have the computer run it a bunch of times and really plot exactly what's going on. So there's going to be some new stuff, but then there's a curve like this. So I said there should be some curve like that, where it goes down and then it goes up. And in Python, we can really calculate exactly what that curve is. So the thing that we did today was what I'm calling near neighbor weighted average, which is that green curve. Next class, we're going to learn a cousin of the near neighbor weighted average, which is the Gaussian weighted average, the red curve, which is like very slightly better, if you ask me. And we're going to calculate this kind of root mean squared error versus the parameter, versus delta. And it really does have something like this, and we can ask the computer to please do it. And up to now, this is all done using the exact value, the f. But at the end of this notebook, we're going to do this trick, having a test set that is going to help us figure out this kind of thing. And when you have a test set, you can estimate the curve. So the true error is in green over here, and the estimated error is in red over here. And okay, they're not great, right? Like the estimated error is quite a bit different than the true error, but they have minimums that are approximately in the same place. So when you go to pick your parameters, this is how we're going to do it. That's all going to be next class. We're going to go through this notebook together. Since we're going through a Python notebook, it would be good for me to know how are your Python skills. And so I have here's my test to see how confident you are with Python. And we're doing everything in this NumPy package. So it's called NumPy. And in NumPy, you can have arrays and matrices, and they're quite fast. And here is a sample problem you might have to do. Make a matrix whose ij entry is an n by n matrix whose ij entry is I minus j. And I wrote for you the first 3 lines of the program. You import NumPy, you set n to 10, you make m to be a 10 by 10 matrix, and then now you have to fill in the details to make a 10 by 10 matrix. So, and then I gave you my confidence from 1 to 5 stars, because 1 to 5 stars is the official system of the course. Can you easily do this? Do you need to know, look up some stuff, all the way down to you've never programmed? You guys let me know how it is, and I'll spend either more or less time on these programming things. The other thing I will say is that the course also has, so if we go to the course website for the textbook, so statlearning.com, and you go to resources, ISL with Python, and you click on notebook files on GitHub, it has these labs. And for example, the chapter 2 lab, this is not what I want. I want chapter 2, okay, I need to maybe zoom out. Yeah, I want the lab. Chapter 2 lab, it will have a notebook just like the one I showed you, but having kind of the chapter 2 one is introduction. So if you've never seen this stuff before, this will help you with the basic commands, what is printing, 3 plus 5, hello world, stuff like this. arrays, and then eventually gets into numerical Python, which is the main thing we're going to be using, NumPy, and so on and so on. So if you've never seen this stuff before, I really encourage you to go through this. If a lot of people are looking at it, I will try to make some time to go through it with you, or the TA will go through it with you. But you guys just let me know whatever you need, okay? Because like the point of the course is for you to get some kind of starting point. Depending on where you are, that can be different. So you guys let me know how your Python is, and then we'll go from there. And yeah, if you want to tell me on CampusWire, like how much programming versus math versus data science you want to see, if you want to see more of the programming stuff, we can go through it a little bit more slowly, and I'll show you some of the tricks. But that's all next class. The videos you're going to watch are all about this idea of having a test error and a training error and things like that. It skips ahead in the textbook a little bit. It skips to chapter 5 because I think this is such an important concept. Okay, I'm almost out of time. Any questions or comments? So make sure you put in this answer into Mathematize before you leave. How confident are you to do it? In the last 3 minutes, you could really try to do it. So the way you should run these things, if you go to Google Colab, spelled with one L, because it's a lab, and you click on that, you can hit New Notebook, and now you can program a notebook on the internet. So you don't need any kind of fancy computer, and you can start typing in the program. Import NumPy as NP, and you press Shift Enter to run it. So that runs, and then what do I say? N was 10, was the next line, and then M is the matrix of a 10 by 10 matrix. And then please fill in how you would make the matrix N. So you can really try it. If you can do this one, great. That's a good start. For bonus points, try to do it with no for loops. If you can do it with no for loops, then you really know what you're doing, and you will be great. Okay. Questions or comments?
Could you upload the manuscript to our course link?
The manuscript for what?
For those courses.
What do you mean by the manuscript? You're asking me to post something on CourseLink. I'm happy to post on a CourseLink, but I don't know what it is. What do you want me to post on CourseLink?
The manuscript, the formulas with.
These things. So so it's not on CourseLink, but the link to the website is on CourseLink. So if you go to CourseLink and you go log in, okay, well the link is there. So it's going to take me to log in. But the link to this website, the introduction, this link is there, and this has everything written on it. Is that what you want?
No, I don't want the version. I want the manuscript just on the screen. You just teach it on.
I see, the Blackboard.
Yeah.
Yes, okay, yeah, I'm happy to post that as well. Yeah, sure. I can definitely post that as well. And also, if you watch the video, then it'll all be recorded there. But I can also post that as well. Sure. Yeah, no problem. Yeah, thank you. Okay. All right, it's 11:20, so if you have any more questions or comments, please come talk to me at the front. But otherwise, see you guys on Tuesday, and try to brush up on your programming stuff over the weekend if you haven't yet. Your first project is going to have 2 parts. One part is basically doing math and giving me a page like this with some math stuff, an example, and there's going to be another part where you make a Python notebook that runs through a real data set. So that'll also be posted by next class. Okay, all right, see you guys on Tuesday, and have a good weekend.